All right, hello everybody. This is the last lesson of Unit 2, and we are going over valence shell electron pair repulsion theory and bond hybridization. So today you should be able to use Lewis diagrams, VSEPR theory, bond orders, and bond polarities to explain molecular structure and electron properties. The essential knowledge for today is that VSEPR theory predicts molecular shape by electron pair repulsion. Lewis diagrams and VSEPR together explain geometry, bond angles, bond energy, bond lengths, dipole moments, and hybridization. And then hybridization is going to set bond angles. So for example, if you have an sp hybridized molecule that only has two terminal atoms with no lone pairs on the central atom, so that is going to give you a 180-degree angle. You also need to know that bonding occurs when orbitals overlap. Sigma bonds are stronger than pi bonds because they are a head-on overlap collision of the orbitals, whereas pi bonds are kind of coming from the side, so they're not a head-on overlap, so they're a little more reactive and a little more unstable. And so those sigma bonds, since they are stronger, they have a higher bond energy. And those pi bonds are going to prevent rotation. So if it's just a single bond between two carbons, technically those carbons can then rotate on that single bond. But as soon as you add a pi bond, then that carbon can no longer rotate. And then here are just the exclusion statements for this specific lesson. Because there are so many, I wanted to put them on here in case you wanted to read them. However, in conclusion of all of those exclusions, there is no need for you to draw or derive hybrid orbitals, so you do not need to worry about that for the exam. When we're talking about hybridization, the only ones you are tested on are sp, sp2, and sp3. So no d orbital hybridization will be on the AP chemistry exam. And finally, no molecular orbital diagrams or anti-bonding or bonding distinctions. So within a covalent molecule, you have two types of bonds. You have sigma bonds and pi bonds. A sigma bond is the first bond formed between two atoms. It comes from the end-to-end overlap of the orbitals along the bond axis. So if two atoms come together to share an electron, that first connection that they make, which is a head-on overlap, would be the sigma bond. Pi bonds are different because they are formed from sideways orbitals, not the direct overlap of the orbitals. So they happen above and below the bond axis. And because of that, since it's not a head-on collision where they are completely overlapping, they are weaker than sigma bonds. And pi bonds are only going to show up after a sigma bond. So if you have a double bond, for example, that means you have one sigma and one pi bond. If you have a triple bond, that means you have one sigma and two pi bonds. So in this molecule ethene here, the carbon-to-carbon double bond has one sigma bond and one pi bond, and each carbon-to-hydrogen bond is a sigma bond. So in the molecule COCl2, how many sigma and pi bonds are present? So we know when we have carbon, we're going to put that right in the middle of our Lewis structure because it forms four bonds. Then we have a terminal oxygen and two terminal chlorines. Now we know oxygen wants to form two bonds and have two lone pairs, and chlorine wants to form one bond and three lone pairs. So we're going to go ahead and start with that and then double check that we have all of our electrons. We know oxygen has 6 valence electrons, we know chlorine has 7, and we know carbon has 4. So that would be a total of 24 valence electrons. So we're just going to double check that we have all 24 before moving on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 2 would be 24. So this has all of our electrons, so let's double check that everything has a zero formal charge. Remember, if it is bonding how it quote-unquote is supposed to, then it's not going to have a formal charge. Remember, our halogens have 7 valence electrons, so chlorine 1, 2, 3, 4, 5, 6, 7. So it wants to have those 3 bonds, or 3 lone pairs and 1 bond, and both of our chlorines have that. Oxygen is a group 16 element with 6 valence electrons, so 1, 2, 3, 4, 5, 6. So it wants 2 bonds and 2 lone pairs. Now, does it have to have that at all times? No, but that is the ideal setup for oxygen. And the oxygen in this molecule does have that. And then carbon has 4 valence electrons, so it just wants 4 bonds. And this carbon here has 4 bonds. So since everything is bonding the way that it wants to, I know there is a 0 formal charge on any of the atoms in this molecule. So we can know for a fact that this is the correct Lewis structure. So now let's go ahead and count our sigma and pi bonds. So we know a single bond is always going to be just a sigma bond. And then a double bond would be 1 sigma and 1 pi. So our answer for this would be 3 sigmas and 1 pi bond in total for this molecule. So hybridization can sound complicated, but it's really just orbitals mixing to make bonding easier. Now, atoms don't want uneven orbitals when they're bonding. Instead, what they do is they blend their orbitals into new ones that are equal in energy and arranged in the correct shape for bonding. So let's look at BeH2 as an example. Now, beryllium is one of our odd elements in the fact that it looks like a metal, like it will partake in metallic or ionic bonding, but it can bond covalently. So if we look at beryllium on the periodic table, it actually has 2 electrons in the 2s sublevel, but when beryllium covalently bonds, it's going to pop one of those electrons into the 2p orbital. So we have 2 separate orbitals ready for bonding. Now, what is hybridization? What I mean by hybridization is you can see we have an orbital coming from hydrogen, which is the 1s orbital, and we have an orbital coming from beryllium, which in this case is the 2s orbital. So this would be 1s, this would be 2s. And then we have the other beryllium electron. Remember, we moved it up to a 2p orbital. And then this hydrogen also has a 1s orbital. So when they overlap, remember this is the sigma bond, this is a head-on overlap of the orbitals. They're going to hybridize into a new orbital. And how we get the name of that new orbital is we look at how many total bonding sites we have. Now, when these overlap and we form a sigma bond between each beryllium and each hydrogen, that means we have 2 bonding sites. We have a single bond here and a single bond here. That means we have 2 sites for hybridization, which means we need an s orbital and a p orbital. So this hybridization for this molecule would be known as sp hybridization. So now instead of all of these different names for the orbitals, we now call them sp orbitals, and they are hybridized because they are coming from 2 separate orbitals that we overlap together and formed a new name for that. Using the image above, which of the following correctly identifies the molecular geometry and hybridization of the C1 atom in a molecule of fructose? So C1 is here on our fructose molecule, and we can see that there are 3 bonding sites. So if there are 3 bonding sites and we are doing a hybridized orbital, we need 3 total orbitals, which means we need s and 2 p orbitals. Because remember, when we're thinking about all of the available orbitals that we always have 1s orbital, we have 3 p orbitals, we have 5 d orbitals, and we have 7 f orbitals. So it goes in order. So if I need a total of 3, I'm starting with s, and then I'm taking from p. So if I need a total of 3 orbitals, I will have s and 2 p's, also known as sp2 hybridization. So sp2 hybridization means I have 3 bonding sites on my central carbon. And since this is 3 actual bonds and not lone pairs, and there are no pairs on the central atom, that means I have 3 terminal atoms and they are all on the same plane. So this would be trigonal planar with a hybridization of sp2, which is D. All right, so valence shell electron pair repulsion theory can predict molecular geometry, and all it's doing is minimizing the electron to electron repulsion. So essentially, when you have these atoms and all of them have valence electrons, they want to get as far away from each other as they possibly can because they're going to repel each other. So what that means is we can predict what these molecules are going to look like. So let's say we're looking at a molecule with a central atom and it has 2 terminal atoms, like this one here. If we have 2 terminal atoms and no lone pairs on that atom, that means all that shape can be is linear because we only have 2 terminal atoms pulling and they want to be as far away from each other as they possibly can. And the farthest they can be away from each other is 180 degrees. So this hybridization would be sp hybridization because it only has 2 bonding sites, so we only need 2 hybridized orbitals, or s and p. And it would be 180 degrees because it would be a linear shape. Then moving on to a central atom with 3 bonding sites, this can be one of 2 things. We will either have trigonal planar, meaning that we have a central atom with 3 terminal atoms and no lone pairs on the central, which is what is shown here, or we will have a bent molecule, meaning we have 2 terminal atoms and a lone pair, which is shown here. Then we get to 4 bonding sites. That can either mean we have a central atom with 4 terminal atoms, or we can have a central atom with 3 terminal atoms and 1 lone pair, or we can have a central atom with 2 terminal atoms and 2 lone pairs. So you see how all of those have 4 bonding sites? It just looks different in terms of whether those bonding sites are lone pairs or atoms. All right, so according to our very first slide in the video, you do have to know the hybridization of all of these molecules on the right here. You have to know their bond angles. You have to know their molecular shape. So this table is something that when you are studying, it is a great tool for you to use because it has all of the information you need to know for the AP chemistry exam. Now, beyond sp3 hybridized molecules, all you need to know is the shape of that molecule. And these are going to be the shapes you need to know, specifically trigonal bipyramidal and octahedral, because the other ones are on the previous slide. So all you need to know is if you have a central atom with 6 terminal atoms, it will be octahedral. If you have a central atom with 5 terminal atoms, that will be trigonal bipyramidal. So all you need to know is those structure names. You don't actually need to know the hybridization or the bond angles. All right, and the last thing I want to teach you for this lesson is electron domain geometry. So the difference between electron domain geometry and molecular geometry is for electron domain, you are going to count any lone pairs as you would a bond. So let's talk about water. So water has 2 single bonded hydrogens connected to an oxygen, and the oxygen has 2 lone pairs. Now the molecular geometry would be bent because we have a central atom with 2 terminal atoms, and because there are lone pairs on the central atom, it's going to pull it in a different direction because of the repulsion between all the electron groups. So that would make it bent for the molecular geometry. Now for the electron domain geometry, there are a total of 4 electron domains, 2 lone pairs and 2 bonds. So we're going to count all of those as bonds, which would mean we have 4, and that would give us a tetrahedral electron domain geometry. Now let's try the same thing for NH3. NH3 has 3 single bonded hydrogens to a central nitrogen, and there's a lone pair of nitrogen. Now we know the shape of this, there are 3, so it's going to be trigonal, and there is a lone pair, so it's going to be pyramidal, trigonal pyramidal for the molecular geometry. Now for the electron domain geometry, remember we are counting this lone pair as a bond. So again, tetrahedral because there are 4 bonding domains. Now let's do one more. Let's do BH3. So remember, boron is one of those incomplete octets. There is not a lone pair on the boron, which means this would be trigonal planar. Now, if they asked you for the electron domain geometry, there are no lone pairs on that boron. So the electron domain geometry is the same as the molecular geometry, which would be trigonal planar. The molecular geometry of the hydronium ion is best described by which of the following? So hydronium is H3O+, which means I have an oxygen in the middle. I have 3 hydrogens connected to that oxygen, and then I'm going to need an octet around oxygen, so I'm going to put a lone pair on oxygen. So if I add up all of my electrons, I know oxygen is 6, and then each hydrogen has 1, so that's a total of 3. And then that plus sign means I lost an electron. So I have a total of 8 valence electrons, and that is what I have here. Now it says, what is the molecular geometry? And that is going to be trigonal because there are 3 terminal groups. And it's going to be pyramidal because that lone pair of electrons is going to repel those hydrogens so that they're going to be as far away from each other as possible. So that means this would be trigonal pyramidal. The shape of the molecule can be determined from its Lewis structure. Nitrogen trifluoride is shown in the diagram below. Which of the following choices has correctly identified both the hybridization of the central atom and the molecular geometry? So again, we have a central atom with 3 terminal atoms, which means we know it's going to be trigonal. Remember, the difference between planar and pyramidal is that planar does not have a lone pair on the central atom, and pyramidal does. So this would be trigonal pyramidal because we have that lone pair on the central nitrogen. And if we're looking at our hybridization, we have 1, 2, 3, 4 bonding sites, which means we need 4 hybridized orbitals. So we need 1 s and 3 p orbitals. So this means that the answer to this question would be D. What would the molecular geometry of the OCS molecule be? So we know carbon is going to be in the middle because it is carbon and it makes 4 bonds. We know oxygen wants 2 bonds and 2 lone pairs. And sulfur is in the same group as oxygen, which means it has the same kind of bonding structure because it has the same number of valence electrons. So we're going to bond sulfur the same way we did oxygen. Now you can see here, everything is satisfied with an octet, and everything has what it wants. So all the formal charges are 0. So now we can go ahead and look at the geometry. Is there a lone pair on the central atom? No, there is not. Because there is no lone pair on the central atom, O and S want to be as far away from each other as humanly possible. And the only way they can do that is being 180 degrees away from each other. So this would be a linear molecule. So the answer for this one would be A. I hope this lesson helped you. If you have any questions, please let me know. I'm always happy to help. Have a great day. Bye.